This is the practice quiz and review for concept quiz 22, which is log functions and log graphs. So the first few questions are solving log equations. In part A, we have log base 2 32 equals x. So we're going to follow the snail pattern, 2 to the x equals 32, and rewrite it in that exponential form. 2 to the x equals 32. I know that that exponent x must be equal to 5. In part B, same pattern, 3 to the negative 2 must be equal to x. A negative exponent is going to give us the reciprocal of 3 squared, which is 1 over 9. On part C, same pattern again, 3 to the 4th equals this entire expression. 3 to the 4th is 81. So we have a linear two-step equation here. Add the 4 to the other side, then divide by 5. 85 divided by 5 is 17. Alright, now when we look at part D, we have another log equation, same process. So 6 to the second power is going to equal this expression here. And we have a quadratic equation here. So in order to solve this quadratic, we're finding the x-intercepts, which means we're going to set this equation equal to 0. X squared plus 9x minus 36 equals 0. So let's see if we can factor that. So this will be positive 12 times negative 3, and 12 minus 3 is 9. So this factored out would be x plus 12 times x minus 3. And the zero product property will give us x equals negative 12 and x equals positive 3. So the only solution here that would be valid is negative 12. Letter E is find the inverse of this equation. So we know that an inverse is when x and y get switched. So y becomes x and the x becomes y. Now, we don't usually write equations as x equals. We want the equation to be y equals. So my end goal here is to get this same equation in a form where it can be y equals. So in order to do that, I need to isolate this log. Eventually I want the y to be isolated. So first I'm going to add the 1 over. Now if I'm trying to isolate y, I have to rewrite this in exponential form. So 4 to the power of x plus 1 is going to equal this expression. So 4 to the power of x plus 1 equals y plus 2. I still don't have the equation as y equals. So my last step here is to subtract the 2. So y equals 4 to the x minus 1, or x plus 1, and then subtract 2 from it. So this is the inverse equation. Let's look at the next few questions, which are referring to graphs of logs. So if log x plus 10 was graphed, what would be the equation of its asymptote? So rather than having to figure out what the graph of this actually looks like, algebraically we know that an asymptote is where the graph is approaching but never actually going to hit or equal. So when we look at a log expression, we know that if we were to write, and this is a base of 10, so I'm going to put a blank here, we know that 10 to the y will equal something. Well, this graph is never going to end up reaching 0 or any negative number, because 10 to the y will never give you a 0 or a negative. So the graph is approaching 0 and it will never hit 0 and it will never become negative. So without having to graph this, we're actually looking at what's going to make the argument here, the x plus 10, become 0. The only value of x that's going to make this equal 0 is x equals negative 10. So the equation of the asymptote is x equals negative 10. This is a vertical line. We know that log graphs always have an asymptote, which is a vertical line. So that brings us to these 4 graphs. The first question here is list the graphs that have an asymptote at 0. Y equals 0 specifically. So again, asymptote means the graph is approaching y equals 0, but never actually going to hit it. So let's look at the 4 graphs we have here. We can see that graph A is approaching the x-axis, but never actually intersecting it. Graph B is also approaching the x-axis, but never actually hitting it. Whereas graph C is approaching the y-axis and never hitting it. And same on graph D, approaching the y-axis. So y equals 0 is the equation of the x-axis. So the 2 graphs that have an asymptote at y equals 0 are graphs A and B. List the graphs that could represent the function f of x equals log base 1/3 x. Well, in order to tell what a log graph looks like, we need to know what the inverse exponential graph looks like. So I know that the inverse exponential graph would be 1/3 to the x, y equals 1/3 to the x, which is a decreasing exponential graph. So I know that this exponential graph could be graph B. But if I want to know what the inverse graph looks like, the log graph, I need to flip this graph over the line y equals x. So if I draw my line y equals x, and then reflect this graph over the line y equals x, we're going to end up with a graph that looks like this, which should be the log base 1/3 x graph. So this graph looks like graph D. So graph D is log 1/3 x. List 2 graphs that could be inverses of one another. Well, we might as well use the 2 that we just talked about here, because we already said that 1/3 to the x and log 1/3 x are inverses. So graph D and 1/3 to the x was this decreasing exponential graph, which is graph B. Or there's another possible answer, because graph A is an increasing exponential function, and if we reflect that one, we end up getting this graph, which is graph C. All right, lastly, list the graphs that could represent a decreasing exponential function. So we already talked about that 1/3 to the x was the graph B, because this is decreasing from left to right, so this is a decreasing exponential function.